We often talk about probability, like when predicting the weather, rolling a die, or exploring the quantum world. The quantum world is fundamentally uncertain. Until we observe a particle, we can't say exactly where it is or how it's moving. All we can do is talk about the probability of where it might be. That probability is calculated using one of quantum mechanics' core tools, the Schrödinger wave equation. A particle exists in a superposition of many states until the moment we observe it. Then it collapses into a single outcome. This is called the collapse of the wave function. But here's the strange part. Nowhere in the Schrödinger equation does this collapse actually appear. Mathematically, this sudden shift has no clear explanation. So what exactly is this collapse, and where does this probability come from? Einstein didn't like this idea of probability. He believed the universe couldn't be so random. And even today, some scientists ask the same questions. One of them is Dutch physicist Gerard to Hooft. He argues that today's quantum theory is vague and incomplete. If collapse is real, he says, it shouldn't just happen as if by magic. It should have a physical explanation. In fact, de Hooft has faced similar contradictions before. In quantum field theory, one of modern physics' most essential frameworks, it's a stunning theory. Its predictions match real experiments to more than 10 decimal places. But there was a fatal problem. Some calculations produced infinities. These weren't just large numbers, they were physically impossible. For decades, scientists have simply cut out these infinities from their calculations without fully understanding why they appear in the first place. Then in 1971, de Hooft mathematically proved that the problem wasn't with the theory itself, but with how we were calculating it. Thanks to that insight, today's standard model could finally be completed, both in theory and in experiment. Now, that same physicist has made an even more provocative claim, that quantum probability and wave function collapse might be illusions of our own making. He argues that the universe runs on perfectly precise, deterministic rules, with no room for randomness. But because we haven't yet discovered those rules, just like we once cut out infinities in quantum field theory, he suggests that we may be temporarily filling those gaps with something called probability. According to him, the world we see is just the surface, just an outer layer. Beneath it, far more complex and far more precise rules may be at work. He proposes that this underlying structure is a cellular automaton. First introduced by John von Neumann and later refined by Stephen Wolfram, the idea imagines the universe as a vast, tightly spaced grid, like a checkerboard. The cells in this grid follow a single rule, one that's surprisingly simple, but through repetition, that simplicity gives rise to astonishingly complex patterns. This might sound familiar: the butterfly effect, chaos theory, fractals. We've already seen countless examples of these behaviors in nature. Complex outcomes from simple, repeated rules. It's perfectly natural, and the results are anything but random. To someone who doesn't know the underlying rules, it may all look chaotic or probabilistic. So, what if our universe is running in exactly that same way? If that's true, if the universe really is one vast machine ticking away like an intricate clock, then quantum probability is nothing more than an illusion, born from our lack of complete information. And wave function collapse is simply the moment we uncover an outcome that was predetermined all along. This is superdeterminism, the idea that our birth, and even this very moment in which you hear these words, were all set in stone at the instant the universe began. Or perhaps, even the birth of the universe itself had already been decided long before it happened. At this point, one question naturally arises. Can we actually test such a claim? According to de Hooft, if the universe is indeed a cellular automaton, then the number of states any quantum system can occupy must be finite from the very beginning. That means, once a quantum computer reaches a certain level of power, there will be a hard limit, a boundary it can never cross. And if we ever do find that boundary, it might be the first real sign that this universe is far simpler and far more finite than we ever imagined. The world we live in is unimaginably vast, the quantum world, impossibly small, and we, caught somewhere in between, continue to wander through the paradoxes of both. So we ask and ask again. Beneath the world we think we know, could an unseen rule be governing everything?